Broadcom, it's always like impressive being in rooms like these, right? So everything about me has been said already. My name is Drotbohm. I work for Broadcom these days. Have been part of the engineering team in the Spring framework for almost 15 years now, and I'm like most known for working on the Spring Data projects within the Spring ecosystems, essentially the repository abstractions in them. And the way that work connects to what I'm going to talk about today is that the repository abstraction is actually a concept coming from the DDD books, and my interest has always been how to make these architectural abstractions workable and usable in application code. And there's a couple of like theoretical discussion, or a bit of theoretical discussion, and a couple of practical examples that I'm going to show you how that idea or these approaches have evolved over the last couple of years, and like essentially what kind of tools you have available today to do exactly that. So with that, I guess you all agree with this statement, right? Who agrees with this statement? So why is that? I mean, I just made it up. I just put something on a slide and you agree. That's kind of nice. But why is that? It's usually, or it is, because while technology marketing is usually around how to build something initially quickly, right? How to build this REST web service with this new framework in under 5 minutes or something. I guess most of us here in the room do not work on purely greenfield software, right? We're busy in that area. So we actually need to build our software in a way that we can actually take it from version 1 to version 1.1 to version 1.2. So what do we actually need, or what's the most fundamental thing that we find in software that allows us to do that, or that lets us stay productive in that space? And it's understandability, right? We need to be able to understand our code. And there's a lot of literature and interesting books surrounding this area. I wanted to pick out two of them. One of them being Feline Herman's book, The Programmer's Brain. She's very close to how we write source code and how we organize source code to actually make it more understandable. There is also Carola Lilienthal, a German colleague of mine. She's written a sustainable software architecture, and she's concentrating more on, let's say, the large-scale artifacts that we find in code bases, and how what kind of means we use in software architecture to make it understandable. Because essentially, we're managing complexity, right? We have to wrap our heads around complexity, and that's what software architectural concepts allow us to do. What are the means and to achieve that? Carola points out three primary aspects. One of them is chunking, right? We talk about modules so that we don't have to talk about like the set of classes that a certain module makes or is comprised of. Hierarchization, right? Let's say, we have our deploy units, we have our build units, in Java we have packages, and we have classes. We're kind of creating a hierarchy of scopes when looking at the individual level, we're able to deal with a limited number of other things that we have to keep in our mind and to understand this and work this. And the third thing being pattern languages, not necessarily meaning pattern in terms of the classical Gang of Four book, right, like a singleton or proxy or what have you, but rather generally purpose pattern languages, stuff like the DDD building blocks, right? Where you introduce stereotypes, concepts, and attach certain rules to them, so that when I say aggregate and you say aggregate, then we're not. I mean, some people say we end up in a giant debate about what that really is, right? But it's at least okay. We have a scope of consistency, and it's supposed to enforce business rules, and then we can discuss how we actually implement that. So the fundamental question stays around, right? We have architectural concepts, and we actually need to turn them into code. Why do we actually need to do that? Well, architectural concepts alone don't really produce working software, right? Or as I phrase this, usually is post-its don't run in production, unfortunately, right? So, except you work at Miro. But the code is the actual deliverable, right, for us to actually produce functionality. So we actually need the architectural concepts to relate to parts of the code base and actually also vice versa, right? So there's a book that has, as I found, influenced the work that I've done over the past decade quite significantly. It's George Fairbank's Just Enough Software Architecture. And I was just reading or skimming through the book, especially this model code chapter, on the flight to Amsterdam, actually, because I read it in 2017 or something, and I thought, okay, there's a lot of interesting ideas in here. Let's see whether we can actually put some of them in practice. And I was like sitting on the plane. I was literally, every paragraph was like directly connectable to something that we actually can now do these days, or it was outlining a limitation from 2012, I think the book is, that he perceived as a limitation to being able to build that bridge. And I was like, oh, we're actually doing the stuff that he's kind of deemed unreasonable or being too much effort these days with parts of some of the technology that I'm working on. So what does he point out in that particular code model chapter? He points out that architecture and code, they differ vastly in various degrees, but they're also somehow connected, right? The first thing is, of course, the level of abstraction. As I said, architecture talks about modules in a logical sense, whereas code is very, very specific. There's classes, there's methods, and what have you. Also, the encapsulation mechanisms are rather abstract in the architectural world with modules, where it's rather technical in the individual programming language. Although some Java, or like the Java ecosystem, have come up with let's say a module system or a concept of modules in the language as well. Right? We talk about different things in domain terms. Here doesn't mean like domain in terms of customer or order or what have you, but architecture in itself is a domain, and code in itself is a domain, right? In code we have a class, we have a method, right? This is like this totally different vocabularies. And as I said, the pattern languages, he identifies them as well, similarly to Carola, that come up with concepts and rules. So, as I mentioned, aggregate, and then there's certain rules surrounding aggregates, how they are allowed to relate to each other, and we're coming back to that in a minute. He then, once he's pointed this out, he points to a paper. It's like this book is really a rabbit hole, right? Here's a paper, and then in that paper you find references to other papers. So there's a paper by Eden and Kazman, Architecture, Design, Implementation, that differentiates architectural and design elements into extensional elements and intensional elements. Sounds tricky, it's not too hard to understand. Extensional elements are elements that you describe by enumerating them, right? And you see that I've kind of placed them in between abstraction and vocabulary. In a software system, you at some point come up with some decomposition strategy, and then you say, here's my order module and here's my inventory module. So you enumerate what kind of parts you actually want to implement. Code is entirely extensional, right? You actually enumerate the order class. You put things in place. Whereas intensional elements are specified, meaning it's exactly relating to this concept and rules thing on the left. Meaning we come up with ideas like there's something like a layer, right? And the layer is allowed to depend on other layers, but not on layers above him or above it. So there is these concepts and rules, and the elements that are intentionally described, not intentionally, are usually much harder to translate into a code base and to make a connection to them. Right. George ends up at coining a term that I've read in this book the first time. I think it's been like popularized by folks like Simon Brown. He's talking a lot about this stuff as well. Architecturally evident code. What is that? It's actually code that represents or expresses the architectural ideas and design, the design intent that it's kind of like been designed for, basically, right? The intent. So looking at the extensional elements, stuff like components and modules, there's a very direct or quote-unquote easy mapping to artifacts in the code world. So we can, of course, have a debate on whether we want to, let's say, or want to implement our order and inventory modules or a shipment as individual systems, right, ending up with a microservices architecture, or whether we want to basically map them to build modules, or let's say just have a way to express logical modules in our application and map them onto packages or what have we. The same applies to just the general business domain language that we use. This is usually reflected. I mean, if you're like been busy with the DDD tactical building blocks, there's usually like a language that you establish, and this is somehow translated into code by naming classes, by naming methods. Fields might be less important because they're like encapsulated already, right? But just coming up with expressing an email address as a value object, for example, is a classical thing that someone using the DDD building blocks would do, right? So for intentional elements, though, I actually came up with or mentioned value objects already, right? So we have these pattern languages, again, DDD or layers, onion rings, or ports and adapters. We're going to look at that later. So how do we actually bake this into our code base? These concepts, right? How do we express that a class is a value object, or that a set of classes form or belong to a layer or an onion ring, or some of them are adapters, ports, what have you. So you can, of course, have naming conventions about them, right? That's kind of that's possible. George, in the book, he differentiates between soft means to establish those connections by using naming conventions, and stronger means, so stuff that can actually be enforced and verified. We're going to get to that in a second. Right, so that the space is pretty like broad here. So we have like strategic patterns, or like what are the things that we could actually try to represent in the code base, like bounded context, like context maps, modules on a strategic level when we talk about DDD, and the tactical ones I've already mentioned those. There's this space of like event-based systems and or event-based communication in between components. And there's this entire architectural space with layers, rings, ports and adapters, command and queries is something similar that we have here. Let's start with the tactical part and have a look at an example here. So just a very simple example. What you see here is an order that contains or consists of a set of line items, and the order like belongs to a customer. Some customer has placed that. Forgive me that I'm using a UML here. It's like I'm a bit busy in the university environment, so I'm kind of used to work with that. So what have we done here? We've there are these model elements these architectural model elements that we've already assigned, or I basically just put them into the UML diagram. So I assigned both the order, the customer, and the line item stereotypes. That's UML stereotypes here. So there's an aggregate. This is an aggregate, or an aggregate root to be precise, and this is an arbitrary entity. Could even be a value, but yeah, just for that sake. So these model elements, as I've mentioned, these concepts have rules attached to them, which means there are certain rules about the way that aggregates might relate to other aggregates. They've been, like, especially when it comes to how to represent them in code, you have to mention Vaughan Vernon's book, Implementing Domain-Driven Design, where he like comes or first formalizes these rules explicitly about how to actually apply them, right? And if we actually apply them to the model, we already find out that there's something wrong here, right? Did anyone see that before I now mention it, right? There is this rule, I think it's first materialized in Vaughan's book, aggregates must not depend on other aggregates except via identifiers, right? So that's something we can do. And that's something we can like logically and manually verify when we work with the model. But it might also be a good idea to be able to, if we can actually somehow bake that information into the code, we can actually do the verification in the code and then get feedback about the correctness of our code. There's a couple of tools that you can use to define concepts and rules with your code base. Like ArcUnit is like I think it's both the Germans, right? It's both a German-led projects. We like order. We like things to be. We like think. Oh, I'm sorry. I jumped back. We like things to be on time as well, but that doesn't work out especially with the barn. But it's interesting. Why are you laughing? It's interesting that there's apparently this interest in verifying code and coming up with rules on the code basis. So what do these tools look like? With jQAssistant, you're basically persisting the AST of your code into a graph database, Neo4j, and then you define queries that both mark or define the concepts and the rules. Right? You don't have to fully understand this, but it's kind of what it's doing here is it selects a certain set of types within the types that it has persisted or scanned and added to the database in the first place. And for all the ones that match that criteria here, it adds a label to them, right? It marks a certain set of types as aggregates and returns a bit of information. What's remarkable here is that in this case, how does it know how to find an aggregate in the first place, right? We actually have to teach it. And what we're doing here, and we're going to come back to that in a second as well, is that this, in this case, represents or references a Spring Data repository base interface, right? So we make use of a particular technology to identify the logical concept. That feels a bit backwards, right? The idea here is that if we find an entity, I think that's we look at the repositories because a repository by definition manages aggregates, and there's a generic type structure in the repository type, and we find out, we take the first one here, the index 0, right? Which is neat because that gets the job done, but it's kind of like it just worked with Spring, and we have to come up with it ourselves, right? The second step that you can then do is basically use the information that we've created here. There's an aggregate, and we can then basically say, oh, if we have an aggregate and that has a field, that's an aggregate return, then we return these elements. And the rules kind of work that way that if the query yields any results, those results are a violation, right? That's kind of the way it does. It's extremely powerful. You usually integrate it in a build step, and it can not only, it's especially powerful because it can not only look at your source code, but it can also scan through your Git commit history, and you can do all kinds of correlations, like which commits touched which parts of the code base, and define rules about all of this kind of stuff. So extremely powerful. It takes a bit of getting used to, especially if you're not familiar with Neo4j and the Cypher query language, but I mean, that's something, okay, if you want to do this, then that's a nice tool. Similar tool is ArcUnit. ArcUnit is entirely Java-based. The idea is that you formulate the rules, you both identify concepts and formulate the rules in Java code, right? There's an API that I've neatly hidden within the aggregates extractor class here. That's basically a customization of ArcUnit, how I tell it to find all the aggregates. And then there is this rule that I can put here, right? This is where we establish the concepts, and then we establish the rule in all aggregates should not refer to other aggregates, and then we check the types of our project. That's kind of neat. Again, it's, I think, a bit more approachable than jQAssistant because it's plain Java. You can just write a test class, you can execute the classes, the tests, or the verification as part of your tests. But it, of course, is more limited to defining rules about the actual code base, right? So let's zoom out a bit again and have a look at what we've kind of done in both of these examples, right? We had our user code, we had these architectural concepts and the rules attached to them, and there was technology involved. The Spring Framework repositories were referenced, and there were tools that we were actually using to teach them how to actually identify the concept and the rules. That's kind of the way that we've worked, right? So the concept definition is actually rather residing on the tool side. So as you've seen, there was no unique expression of something is an aggregate. We had to formulate how to identify the concept in both the jQAssistant way and the ArcUnit way, right? Both the concepts and the rules were defined by referring to like both the tool and the Spring Data repositories. And we were responsible to define both of them, right? We defined how to find an aggregate in the first place and the actual rules surrounding it. So that enables us to do what we kind of want. It's just that if you start a new project, I don't think the first thing you want to do is actually come up with, okay, we need to decide on the tool, and then we actually have to find out how we identify the concepts that we want to use, and then define the rules, and do this over and over again, maybe copy the stuff from another project that if maybe used DDD building blocks in your code already. So what can we do about this? So let's assume we had some kind of magic superpower, something we could actually use to actually embed these concepts in the user code directly. So that all we need to do is just express that this order is supposed to be an aggregate root. And by that, we can actually prepare the tools externally, or we can prepare reusable extensions to certain tools that then find the concepts in the code base and actually also implement the rules that are supposed to be verified. So they could be provided by the tool/framework vendors to actually integrate with that. Right, the framework vendors as well. So one of the projects that I've been involved with for a couple of years now, and that's been kind of the result of a discussion of these topics at various conferences, is the jMolecules project. And the idea was, it's primarily driven by Stefan Pirnbaum, actually one of the guys behind jQAssistant, and Henning Schwentner. He's a colleague of the aforementioned Carola Lilienthal. We are thinking, okay, what if there were like programming language specific means to express these architectural concepts in the code base, right? And then I'm working primarily in the Java space, so I was like, okay, let's have this jMolecules thing, and Henning was like, oh, no, we need to touch .NET as well, and PHP or whatever. The reason that I'm spending a bit of time on this project, especially the jMolecules one, and that's why it, compared to the other projects, is a bit more farther ahead in terms of like integration with various tools and frameworks. But if there's anyone working in the .NET or PHP space, please reach out to me. We're looking for people to get in touch with, to populate these ideas in other programming language communities as well. All right, so what does it do, right? Let's start with basically a representation of the order example that I've shown you. I've already added a bit of mess to that, right? You see some JPA annotations, and there's like Lombok involved here. So you can argue that there's not much of the like domain kind of left. It's like a bit of the forest for the trees here. And what can we do about this, right? So the first thing we can do is, that this jMolecules library allows us, is to use types to actually express the architectural role of a type in the type system, right? So we can actually implement a marker interface aggregate root, and that then in turn already has generics declared so that it actually requires the identifier type to actually implement identifier in turn, right? So this is the idea behind that, is that we use the type system and the kind of restricting means of a type system to already, like for one, of course we can think about this as some kind of validation that the order ID is really an identifier, but it has some viral effect on the code base, right? That we kind of promote these types into other related types. The primary idea being, we don't actually need, for some parts of the verification, we don't even need extra tools other than the ones that we already use, and the compiler is actually quite helpful with that, right? So we get a bit of base verification for that. So with only that in place, we can already get a step ahead, because we can now, in jQAssistant, we don't have to formulate all the queries and all the Cypher stuff ourselves, but we can simply use the predefined, oh my gosh, dependency that you just hand into the plugin. So jQAssistant allows you to prepare those rules in consumable jars, and then you basically use them in a way that I've shown you here, right, with Maven. And there's a bit of configuration where you can enable different levels of verifications by that. With ArcUnit, it's kind of the same. There's just basically a class that gives you access to a factory method that produces this ArcUnit rule. And in this jMolecules DDD rules, there is like a couple of things, like value objects must not depend on entities, and all these kind of model-specific rules, including the one that aggregates must not depend on other aggregates except via identifier. There's a bit of a recent development that we were looking, okay, this still requires you to either execute the tests or even the entire build to get the feedback. And I've been experimenting with a bit of, there's some API in Java, the annotation processing toolkit, that basically hooks into the compiler, so you actually get a chance to post-process all the classes that have been part of a compile step, which is usually used to generate downstream source code, which is then compiled again. But you can also, in that very step, you can attach additional compiler errors to an existing class, right? And that's basically what I'm doing here. You see, I've kind of artificially introduced the same mistake that we had in the example before, so that order is an aggregate root, and it still references the customer, which is an aggregate root itself. That's not on the slide here, but down here it basically says what I've printed out in the back. So invalid aggregate root reference. It's exactly the error message that you would get if you ran this via jMolecules or not jMolecules, jQAssistant or ArcUnit. Right? So there's an additional dependency, a jMolecules APT dependency that you put into your project, and you get basically your compile-time verification of your DDD model. So the question that usually comes up is like, if I have this, why would I use the other tools? One of the cases where you would basically refrain from using that versus the others is if you have an existing project and you would want to gradually introduce these verifications, and you end up with like the code not compiling anymore, right, with this thing, because that's the strictest flavor you can get of this. Whereas the other tools allow you to basically limit the set of classes that are checked. ArcUnit has a way to kind of freeze the rules, so you can run it once, it captures all of the violations, and then it only barks at you if you introduce new violations, right? You can basically say, okay, we don't care about the current code, but whenever I change stuff, when I add new code, I don't want that to appear here, right? So there's another thing that I want to just briefly touch upon before we move up the stack a bit, is that the expression of those concepts allows us to get rid of a bit of boilerplate code that you've just seen here in the examples. So with the concepts and the rules are usually, if we're thinking in onion architecture, are usually located both in the domain core and the application ring. That's where you basically represent your domain abstractions, and your application rules, services, what have you. There is this infrastructure ring around the application ring that then kind of touches into, let's say, database access or web APIs, right? So this is where frameworks like Spring, JPA, or Jackson come into play. And there's a certain set, or if you follow, let's say, or if you use, let's say, a lot of value objects in your domain, or these aggregate structures, those has an effect of how you actually need to teach, let's say, Spring Framework that it can actually resolve an identifier that you send via a web request. It can actually automatically resolve that into the full aggregate instance for you. So there is some integration points with technology frameworks. And one example that I've basically pulled out here is that in this example, there's a lot of boilerplate induced in the class by JPA, right? We need to add all kinds of metadata to get that class mapped onto a data store, right? And this is rightfully frowned upon by like DDD people. Like you don't want your application or your domain entities to be dependent on JPA, whereas like annotations might be the slightest form of dependency here. But there's other stuff in here that's even like more problematic and subtly problematic, right? JPA requires you to have a default constructor, which kind of somehow subverts our ability to keep fields non-nullable and whatnot. So, long story short, tag bleeds into your code base, and the question is, or most of that, or not most, almost all of the annotations, the JPA-specific annotations in here are kind of, they're not really like room for creativity, right? Because if this thing really is an aggregate, there's not so many ways that thing could be actually mapped to a relational database, except you have an existing database schema that you need to adhere to. But if you start from scratch, then this is kind of, there's a certain kind of rules, like references into collections of entities always have to cascade, and they also have to use auth and delete and whatnot. Certain rules that kind of apply to a technology projection of a certain architectural concept. So we can go ahead and basically attach again the metadata to the class, and we've also changed the simple customer ID reference to something we call, or we have in jMolecules called an association. And with that, we can actually get rid of all the JPA metadata by using some code generation in ByteBuddy that we would actually, when you compile your code, it would actually add the persistent-specific metadata that's needed to your code, right? There's support for that for JPA, for JDBC, for MongoDB, so we're not kind of just focused on one of them. So the idea fundamentally is you express something in your code that's in this order as an aggregate, and we make sure that it correctly maps onto some persistence mechanism that you chose. Right? So basically, this is where you started. This is what you get rid of, and this is what you end up with, which already looks like much cleaner, right? There's a bit of Lombok-induced boilerplate. Oh, and there's this one special thing about order, because order is a keyword in SQL, so we need to either quote it, or in this case, I just thought, okay, it would be nice to rename the annotation, and it kind of you end up in a much better place, because that customization, that's the only thing that's special about JPA in this case, right? And that's the only thing that we end up having to add, and everything else is just being taken care of. Right? And we made, of course, the code more expressible. All right, so we have 10 minutes left. 10 minutes? 50 minutes, right? 15, nice. So with that, it's kind of what you should take from this section is there's like these fundamental building blocks, DDD related, that you can actually express via the type system in your code base, and then get like the verification and the reduction of boilerplate from. If we move out a bit and basically have a look back at the onion architecture, for example, right? We can also have a look at, okay, how do we actually represent that in our code base? Or the question is whether we should actually do that primarily. So onion architecture, for the rest of us, it's basically a domain, core, and application ring around that. So it's basically assigning code to certain logical parts, domain being at the core, application services and whatnot surrounding that, and the infrastructure components being like kind of located on the outer rim of the application. And there's a kind of predefined allowed dependency direction that the infrastructure depends on the application layer, and the application layer depends on, or the ring depends basically from outside to the inside, right? So the fundamental, what I found interesting about any of these separation of concerns architectures, be it hexagonal or onion architecture or what have you, they're kind of telling you how to separate your technical code, everything that's an infrastructure, from your business code, primarily for the sake of testability, which is a good idea. But it's also a bit, like, especially for people working in the Spring ecosystem, like that's kind of what we've done forever, really, right? So, I mean, blame us for all the XML stuff, but we've always incentivized, you write your business code, and then you say, package that in a service, and that's unit testable. And then you have your controller, that's like a separate piece of code that then exposes that functionality to HTTP, for example, right? So the fundamental question is, this is kind of formally describing what we've kind of informally done, especially in that ecosystem for a while already. And we can also raise the question of whether the thing or the problem this is solving, achieving testability, is an honorable goal, I guess, but is this really the primary thing that we need to solve when we're talking about like system decomposition? And yeah, we have basically the infrastructure on the outside. So if we, isn't the primary problem of software architecture here to find a decomposition of your domain in the first place, right? Like we need to actually want to separate the order stuff from the inventory stuff, from the shipment stuff, and what have you. So these architectures do not really care about that, right? And they are not, I'm not saying they do not care, but they're not helpful in achieving that, or basically, yeah, that separation. So how would you actually do that? So if you, let's say, have like two of these domains, order and inventory, do you basically copy the onion, right? So two onions. That kind of, I mean, that's a perfectly reasonable approach. It kind of leads toward, looks like a bit of, we're heading towards microservices, right? So we have like separate systems that all contain the infrastructure and like APIs and what have you, or even like the self-contained systems approach, really, because the APIs and UIs are included here. But it kind of raises the question, how do these things then talk to each other, right? If we need to notify the inventory about like an order that's been completed, then we actually have to go through all of these components or through the infrastructure, probably a message broker. That works fine, can nicely be mapped to a microservices system. However, do we really want to equate, oh, we want to decompose a domain with, we always need to do microservices? That's probably not the case. So a different approach could be like, okay, let's just have multiple domains inside here. Does that get us very far? Probably not, because there's like domain-specific code in each of the application rings. There's probably controllers and repositories that relate to certain domain abstractions. So what else can we do? And who likes to prepare food? What's the best part of prepare? I have a task when I'm at home and we're cooking, and then there's like one task that I'm kind of feel, or I seem to qualified enough to be tasked with that, which is cutting onions, right? And the idea is as follows, and it's usually involving tears, is we basically cut the onion, and by that we kind of open up parts of the application ring to the, not necessarily to the outside, but to potentially other cut onions, right? And if we get to that kind of arrangement, we can just like wrap this in a nice shrink wrap, and then we kind of package these individual onions in an application, and then it could be just like a modulithic arrangement. I guess you see where I'm heading, because in the end, what happens inside of these boxes, inside of these green boxes, doesn't really matter anymore, right? So they could individually expose, let's say in the Spring space, Spring Beans, like object references that we could call from one module to another, or it could expose events, right? And I mentioned the word already. It's not really about like onions or hexagonal or ports or adapters on that level of arrangement, but it's like we have individual modules, right? Logical modules. And whether you use onion architecture to technically decompose them internally is an implementation detail to these individual modules. And it can be, even in a monolithic arrangement, the same way it can be an internal arrangement in a microservices environment. So that's kind of leading towards the project that I'm currently working on. I don't want to give you a full overview about this, but rather connect basically all the ideas that I've basically presented to you already, to how this basically maps into the Spring world in more detail, and how we can actually, just to give you a rough idea of what it's trying to achieve. There is, as your standard Spring Boot application, right? You have your, it's located in some package here, com.acm modulith, and you can then go ahead, or what it kind of does, it implies that all the direct subpackages form the entry points into a logical application module system, as we call it, to application module system explicitly, because there already is a Java module system, which has kind of different goals and kind of does other things, like certain things much better. It can integrate on the JVM level and basically allowed the JDK team to decompose it into individual artifacts. But it also doesn't, and for a reason, doesn't actually consider, let's say, application level developer concerns like creating documentation about this, making tests easy or whatnot. We're going to get to that in a second. So there's a Spring Boot specific kind of idea of how you structure your application into logical modules, and it allows you to have code that's exposed to other modules and code that's hidden from other modules. It doesn't have, these packages don't have to be named internal. It's just that every sub-package of these base packages here is just kind of hidden by default, and there's means to actually design the API of a module, quote unquote. Also, important difference to the JPMSs. We can have multiple logical modules inside a very jar. Right. So what do you need to do to actually get the relationships between the modules verified? There's again a test class where you say application modules of point to the main application class. So that's the Spring Boot application class, and you just call verify on them. And then you basically, we are using ArcUnit under the covers, and you get these ArcUnit rules that you would have to write manually. Module A is allowed to to depend on classes of module B that are reside in a certain package, automatically basically applied to your code base. Right? That's kind of the idea for the verification. We also extend that into testability when it comes to Spring. So with the Spring Boot, you actually can horizontally carve out slices of your application to only test those, right? So there's web MVC test to only bootstrap controllers, and data JPA, data Mongo test that only bootstraps repositories. And that's already kind of a reflection of a similar idea that we started with, right? So the stereotype annotations you find in Spring Framework achieve the same, kind of the same goal, and they were developed in the same spirit, so that you logically assign a certain role to a class, and then the framework in turn uses that assignment to find out which components to bootstrap. The reason we kind of moved or started this jMolecules thing in parallel to that was that, for one, why does it have to be Spring specific, right? And the other thing is that Spring naturally doesn't have any kind of interest in like being or allowing you to express like other like DDD concepts or what have you, right? So there's a natural limitation of what the framework is interested in, and this is usually horizontal layers, because the framework is interested in applying technical guidance on these layers, right? Controllers are basically exposed as URIs through your web server, or in data accesses, there's like exception translation from JDBC exceptions into a general purpose data access exception hierarchy. So if Spring Boot can do that with the module package convention that we've established in Spring Modulith, we can also basically allow you to carve out tests horizontally. So there's an application module test annotation, and then if you locate an integration test in basically the very same package, then it would only bootstrap the vertical slice for you. The final thing is that we can look at the components look at the modules as some kind of component, right? They're kind of encapsulating stuff. They have a provided interface and a required interface. So provided is the API, but required is everything that is required, as the name suggests, or the term suggests, required by other modules. And we can actually go ahead and, with the help of the jMolecules abstractions that you could use in your application code, we can find these things, right? We can find like exposed services, like if you use in this case, Spring Framework stereotype annotations, but there's also the DDD service annotation is available in jMolecules. Aggregates you have seen. There's also a marker event for domain events to express those, and we can then basically do the same thing for the required interface. There's a Spring Boot specific specialty in here for configuration properties, right? That's like an architectural term to some degree as well, but it's kind of reflected in Spring Boot as a certain mechanism how to implement external configuration. And there's also, of course, the consumed events, right? We have event listeners and a means to express something is supposed to listen to an event in the code base. And because that information is available in the code base, we can kind of extract it, and from the 500 classes that you have to deal with in your application, we can just pull out the ones that are quote-unquote interesting or interesting to be documented because they form an API. And then we can actually create, this is like from a university project I'm doing it with the TU in Dresden. It's just a sample project that the students get to write applications with. But it's kind of considering each module as a UML component here, writing out a component diagram with different kinds of relationships in there. There's an overview diagram that we create. There is a diagram that just carves out a subtree of the overall tree to basically, in this case, show, oh, if I want to understand the inventory, then these are the direct dependencies that I have, and this stuff is all like pulled out of the code. And we also pull out what we call application module canvas. It's like a textual description in originally ASCII doc that then can be rendered and produces that table in which you see, oh, we find like all the Spring components by stereotype. So if you were using, that's probably interesting to mention here, if you were using, jMolecules has means to express onion and hexagonal architecture. So if you were declaring your classes at this class is a port and this class is an adapter, you would not see service and controller here, but you would see port and adapter, right? So we kind of extract the information again that you put into the code base. Aggregate roots, value types, the same stuff. So everything that if you have a new team member coming into your team and they're supposed to change something about the code base, you can actually point them to that kind of stuff, and it gives them a high-level overview without the need to immediately jump into the code base. And all of that documentation, the nice thing about it is it's by definition it's up to date. I'm not saying it's correct because like, it could be stuff in there, but it's a direct reflection of the code base that you generate basically through each build. All right. So with that, we just basically we're putting architectural concepts in code. There are means available in the form in the Java space in jMolecules. We're not kind of coming up with new stuff here. There's like pre-established pattern languages that we support, the architectural approaches that I've mentioned, and yeah, jMolecules is the vehicle, and there's like a lot of framework integration, as you've like seen in a certain way. And with that, yeah, there's a paper that we've written on jMolecules in particular. It kind of summarizes basically everything I've said like in the last 50 minutes in a five-page document. And there's going to be a book coming, hopefully end of this year. I've been saying this for quite a few years already. But books are like software, right? They're always late. But I'm confident and I'm making progress. That's nice. And with that, of course, links to the projects. There's a GitHub community. There's a lot of books in there, papers. And I think with that, I'm done. Thank you for your attention and enjoy the rest of the conference.